Today, our first presenter and project coordinator, Lars Rausendahl from Aalborg University, who has done a brilliant job of everything in this project. So thank you very much. I'll be keeping time. So if you hear me saying time's up, don't be offended.
Thank you very much, Emma. I'll see if I can live up to that. So thanks, Emma, and a very warm welcome from me also to everyone here and those who are online. It's a real pleasure to be here today. It's the culmination of 4 years of effort from a lot of people. So it's really a significant event to. I think it's only changing on yours, Emma. Small excitement. As you can hear, we are also having trouble. It's brilliant. Okay, perfect. We have an agenda today which is jam-packed with interesting. We will start by giving some introduction to what we've done and then we have a number of technical. So if you have questions, please wait until the technical presentation. There's a lot of questions that may come up, and I'll be back panel discussion also. So if you think it wasn't answered, then you are more than welcome to ask at that point. We will also have a session with sister projects today. So we will have a presentation from PNNL in the US. We'll have a presentation on an HTL project in Denmark, and then we'll have a local presentation from Amsterdam on HTL on waste plastic. So I think we will cover a lot of aspects during the day, and not to waste all the other presenters' time. Let me start. Let me give you an overview of what this project was about. So it's a project of 11 partners, 7 countries, 5 million euros, and 4 years. And we set out with an ambition to address the circularity around our cities, the thing good for the environment. The way we envisioned to do it was to look at representative urban feedstocks. So you can see we have both slide food waste and construction wood, different types of feedstock. Looked at different pretreatment for these feedstocks. Set up an conversion on the organic stream, and then finally addressing the trash market. And because this was a response to a road fueled, you can also, of course, from the name that was what it was focusing on diesel and gasoline, managed to sneak in marine fuels as well. So in order to do all of that, we set up 8 bullets for the project, so that it wasn't just a technical project, but a project where we tied together technical achievements, technical investigations, with also scenario development, LCA, techno-economics, to get the more holistic approach to setting the stage for HTL as a viable technology for waste valorization in the future. I can see this is very, very small, but these were the overall targets. So we had a target for on economics, that when you look at how much sludge that was available in Europe or is available, we would be able to replace something like 20% of fossil fuels in the European transport sector. We had a potential of a turnover of more than €1 billion for a full implementation of this. We set up targets for the environmental side. Oops, was that me? To convert millions, hundreds of millions of tons of low-grade feedstock into something that has more value. We had an energy efficiency target of more than 70%. And we were targeting, and again, this is a full implementation, something like a 75 million ton CO2 reduction per year if we were to convert all the urban waste in Europe into sustainable fuels by this method. Job creation is something we also targeted, direct and indirect, 50,000 and 300,000. And also this European, my fingers are too big for the buttons. And also this European leadership in renewables, that there was an ambition that Europe should really lead the world in renewable energy. So these were the overall objectives that we started out addressing. So what did we? How did we do? Well, we have spent a lot of effort looking at pre-treatment, not just to make a feedstock that is better for the downstream stuff, but also to see if we could valorize side streams. This has been a big part of the project. We have been operating at fairly large scale, pilot scale HTL. We've processed a lot of sludge. This is so reaching something like 8 tons of sludge. And you can see we had, of course, the Corona break in the middle, but kept going after that. We've been running continuously for hundreds of hours. We've been able to establish that none of the harmful stuff makes it to any of the effluents, so microplastics, medicine, I call it debris. Everything is really trapped in the HTL process. On the other hand, we've also demonstrated that we can recover some of the useful compounds, inorganic compounds, for example, phosphorus, which is also present in the sludge in large quantities. Working at pilot scale, we've been able to, or we've had to come up with a method to take the raw biocrude and transform it into something that could be hydrotreated. And so we've designed and implemented a pilot scale conditioning stage in order to accomplish this. We've looked at water management. Water management is a key part of running efficient HTL. So we've been looking into many different ways of handling the water. This is an example from some of the membrane filtration that we've looked at as an approach to handle this. The raw biocrude has been hydrotreated, again at pilot scale, and this is a very important feature of the project, that we've worked at a scale that I think is first of a kind for HTL projects. We've actually been working at very large scale on all the stages that we've looked at, working with multi-stage hydrotreatment at various sites. We've been looking at new ways of looking at the effect of this hydrotreatment on the product to determine whether, to what extent we were actually going in the right direction. So also looking at new analysis methods. We have generated lots and lots of data. Lots of data at very high quality, very high resolution, and of course complicated again by the scale. The fact that we're working at very large scale. I'm speaking as a university person now, not as an industry person, so I know that there is a difference. But still, we've been working at a scale where it's all of the unit operations have to be linked, and in that linking, it's really difficult to maintain full closure of mass. It's really hard not to lose anything. But we've accomplished that. We've turned that into process models. We've turned that into life cycle analysis in order to establish impacts, and we've looked also at so how do we actually roll this technology out? So one thing is looking at all the technical stuff, but to try to set up a road to market, identify viable placements and infrastructures in order to implement such a technology into the both into the waste management infrastructure and also into the energy infrastructure. So overall, HTL, it's an attractive technology for such waste streams. It has high energy yield. It has a low impact in terms of environmental, in terms of the effluents, and it also has a high potential for this circular use of inorganics. So there are lots of pluses here. One thing also to keep in mind is that HTL is more than just setting up, running something at a temperature. You see a lot of data from batch. It's much more complicated than that. So this whole process design is really crucial and has to be fully aligned with whichever feedstock it is that you are putting into the system. So and you'll see lots of examples of that in the following. There are, of course, challenges. And again, one of the things that happens when you go into pilot scale, you run continuous mode for very long times, you start realizing things that you might not have realized if you didn't do this. One of the things is we have this challenge on deposits in the heating stage of the HTL system. But so that, of course, is a barrier if we can't solve this. But out of all the work that we've done, we've also been looking into this pre-treatment and trying to see if that poses some differences. And this could very well be a workaround, that you actually do the pre-treatment, even though you lose carbon, but you get an enhanced yield. So you remove potentially your problem with the phosphorus, and you don't actually lose much on the overall performance, even though you make a more complicated process. So this is a really interesting thing to look into. And of course, the other thing that comes out of this is that we have much less nitrogen in the biocrude, and nitrogen in the biocrude, you'll hear much more about that, is somewhat of a challenge. A regulatory barrier that we've identified is that a technology such as HTL is a disposal technology in the official classification. And that means that this whole upcycling, this value creation that lies in sending phosphorus on and also making an energy product is not valorized. And this, of course, is an issue on the more regulatory side. So in summary, we've, over the last 4 years, we've addressed a lot of both technical, operational, very much so operational, and regulatory questions, and taking HTL much closer to something that can be an implementable technology. We've identified, as I said, regulatory barriers as well, and also found new topics for R&D. For example, this deposit formation, the pre-treatment workaround, in order to make the process even more optimized. And so, all in all, I think it's safe and fair to say that we've contributed significantly to the maturing of HTL as a viable technology for urban waste stream utilization. We've advanced the associated science, and also we've contributed to this ambition of positioning Europe as #1 in renewables. And I think that I had a couple of more. I had a slide, I thought, that would say thank you to the partnership, but I guess that'll come later on. But let me say it anyway. I think it's been a great effort from all of you. We've had a challenging time in between where we had we could meet only online and not in real life. Luckily, we've had the opportunity for a few meetings. But I think in spite of all of this, it's been a pleasure, and it's been a great effort by everyone. So thank you very much for that. And now I then would like to hand over to the next presenters. Is that you? Right. Iransu Alegria from Sener to talk more about this pre-treatment.
So thank you very much for giving me the opportunity. Hope I will provide you with an overview of what have we done related with pretreatment. Yeah, and yeah, here in this part of the work that we have been performing during this project, not only CENER has been participating, but also I would like to thank Joshua and also the Albert University for the participation and for the sorry. Yeah, I will forget it. So maybe you will have. Yeah, please. Yeah. So let's start. Yeah, the title of the presentation is improving the HTL crude value chain from the very beginning, from the start, and that is the main point of this. Yeah, and I guess that is quite interesting in order to not only reduce the nitrogen content in the sludge, but also by valorizing the side streams. Yeah. So first of all, I would like to start with some rough numbers. Yeah, here in Europe, we are producing now annually around 8.7 million tons of dry sewage sludge. Yeah. Nowadays, by the agriculture sector. Yeah. 7% of it is being. So, yeah, why not sewage sludge for biocrude production? Yeah, quite interesting of it. Yeah, but we know what is sludge has a composition varies from one place to another. And another critical point of the composition of sewage sludge is the content. Yeah, we know that nitrogen content is very problematic compound during the nitroxides. Yeah, so this has to be removed. Normally nowadays it's removed during the upgrading. Yeah, but it's quite difficult to remove them because of their recalcitrancy. Yeah, so why not trying to reduce this nitrogen content before the HTL process. Yeah. So first of all, I would like to present you where the samples that we have been using during the project comes from. Yeah, because they are quite viable. Yeah, they are coming from the 3 different countries. Yeah, from Denmark, from Aalborg concretely, from Germany, and from Spain. Yeah, and also they have a variability in terms of the production. Yeah, for example, the sample from Aalborg is in the form of pellets. Yeah, with a very low moisture content, whereas in the sample of Germany that comes concretely from Karlsruhe comes from a primary sludge. Yeah, that is centrifuged, and normally this sludge is being used for incineration. And in the third case, for example, in this sample of Spain, comes from wastewater treatment plant that is located in a small town, but in the nearby is also there is also agro-food industry. Yeah, we will see how it affects. Yeah, to the composition. We took a deep look into their composition. Yeah, and as you can see, we look for macromolecules such as lipid content, for example, or proteins in the form of amino acids. Also, we look how much fiber the content in terms of lignin or carbohydrate. In case of the in case of the the sample coming from amount of ash, 37%. Yeah, whereas of the sample coming from today, that counted only 16%. The components accounted between 3% up to 80%. Yeah, and what we is that has an impact for the HTL process. Yeah, and when these 3 samples are subjected to an HTL process, yeah, not only it has an impact in the biocrude yield, as it can be seen here. that the sample for Aalborg, for example, the yield in terms of biocrude production is significantly lower compared to the sample of Tudela, but also it varies the composition. Yeah. So we took also a deep look at the distribution of nitrogen in these samples. Yeah. And something interesting is that most of the nitrogen is in the form of organic nitrogen in the form of amino acids. That means amino acids that constitutes the proteins. Yeah, that accounts for around 55 to 73%. Yeah, a mineral amount is in the form of this nitrogen is in the form of inorganic nitrogen. Yeah, in the form of most of it in the form of ammonia. Yeah, that accounts for another 8 to 12 to 14%. Sorry. Yeah, but there is still another part of the nitrogen that accounts for another 16 to 30% of this nitrogen that is in the form of prostatic groups, yeah, such as phospholipids or peptidoglycans, etc. Yeah, and we can see, or what we have been seen is that or corroborated is that there is a variations between these different samples in terms of nitrogen composition and nitrogen distribution. Yeah, if we have a look at the inorganics content, we have seen earlier that the ash content of each of the sample varies quite a lot. Yeah, but in terms of the composition of these inorganics, we would like to remark, yeah, the appearance of phosphorus and its salts. Yeah, most of them combine the phosphorus combined with calcium for forming calcium apatite, or with iron for forming bavianite or stengite, and also the presence of silica. Sorry, of silica. I wanted to, yeah, that comes from sand and minerals. Yeah, so how we address the reduction of nitrogen, yeah, because as I spoke earlier, what we wanted is to remove the nitrogen from the very beginning. Yeah, so for that we apply three different strategies. Yeah, the first one is what we call the chemical pathway. Yeah, and what we did was mix the sewage sludge with an acid catalyst. It was subjected to a temperature around 150 degrees, pressure around 20 bars for half an hour. Yeah, and the outcomes were a solid, yeah, with a less content of nitrogen because the nitrogen was in the soluble fraction. Yeah, similar outcome came for the second strategy, yeah, which is what we call the enzymatic pathway. But in this case, instead of using an acid catalyst, we use enzymes. You know that enzymes are quite specific, yeah, and normally they perform much better under very mild conditions, yeah. On the other, in terms of temperature, no pressure, and so on, yeah. The main issue compared to the previous strategy is that it requires longer residence time. And the third strategy was the combination or the integration of these two previous pathways. Yeah, let's see a little bit which are the main outcomes of these strategies. For the chemical treatment, we reached a solubilization of more than 70% of the nitrogen. And but not only we realized that, we also realized that the solid, the pretreated solid, composition varied in terms of carbohydrates and lipid content. And why is that? Because most of these structures are being concentrated. But not only that, also the use of this catalyst triggered the solubilization of some inorganics, such as calcium or iron, and so on. So it reduced the ash content in the pretreated solid. As for the enzymatic pretreatment, once more the threshold of 70% of nitrogen removed was reached. Yeah, enzymes are quite specific, as I said previously, and they can remove most of the proteins. Yeah, they can solubilize most of the proteins. They require mild conditions, but longer residence time. But what is interesting is that the nitrogen that is released in the soluble fraction is still a protein or peptides. That means a protein that has been broken down into small peptides, or even free amino acids. Yeah, and this fraction can be upgraded, can be valorized. We will see it later. And for the third strategy, we combine one way or another, first chemical followed by enzymatic, and the other way around. What we saw was that the combination of first ensymatical followed by the chemical pretreatment gave us the best results in terms of nitrogen removal, but also the reducing the inorganic amount, content in the pretreated solid. But we know that has some implications, something that has Lasse mentioned before. The first one is carbon loss. I mean, pretreatment, when we are removing proteins, the nitrogen content in protein is as much as 11 to 40% by weight of the protein. The rest are carbon, oxygen, hydrogen, exactly, etc. Yeah. So we know that when removing this nitrogen compounds, we are removing also carbon, yeah? And this carbon loss can be as high as 40%. It depends on the severity of the treatment, yeah? But on the other hand, we know that this fraction can be valorized, can be upgraded. Chart of the HCl process, if we include another means an increase in equipment cost, an increase in cost, and increase in energy demand. So that's something that has to be there. But on the other, the positive point of this is that when this protected solid is to an HCl process, the would obtain improvements not only in yields, yeah, can be accounted to more than 22%, but also in terms of quality. Why? Because on one hand, there are less nitrogen-derived compounds, yeah, such as nitrogen heterocyclic or aromatics. Yeah, but on the other hand, it is the amount of aliphatic compounds, such as fatty acids, are increased. So the quality of the biocrude is improved. And as I mentioned earlier, if we have a fraction with soluble peptides, amino acids, and proteins, yeah, it can be used as a substitute for fossil-derived fertilizers. But not only that, it can be also used as a what is called biostimulant. Yeah, nowadays, the definition given by the EU for the biostimulant is compounds or even can be microorganisms, yeah, that stimulates the natural process for that performs the plant in order to improve the natural nutrient uptakes or the nutrient efficiency or the crop quality by itself. Yeah, so we tested our product. Yeah, as you can see on lettuce. Yeah, we choose two different dosages because we were not aware of previous analysis. We compared it to a commercial biostimulant, and in order to detect easier the biostimulant effect of our product, we subjected some of the plants to a salinity stress. Yeah. So which are the main outcomes? Yeah. On one hand, there were no big differences compared to the commercial biostimulant in terms of biomass production. But something that is quite interesting is that when using our product on the plants that were subjected to this salinity stress, yeah, it was detected that the composition, the nutritional composition was better compared to the other plants. Yeah, and it was detected a higher content in phosphorus, in potassium, sulfur, zinc, cadmium, magnesium, etc. Yeah? But not only that, it was detected that the availability of cations in soil was increased when using this product. Yeah? And for all the cases in which our product was tested, it was seen that there was a higher mobilization of phosphorus in the soil. Yeah? That means a higher availability of phosphorus for the plant. Yeah. So, yeah. As a conclusion, what we have seen from the pretreatment and the pretreated solid that is being produced, on one hand, that the nitrogen content of this pretreated solid is being reduced. The inorganics also are being reduced. But not only that, we have seen that the biocrude quality is improved in terms of yield and on quality as well. And also that some side streams can be upgraded, yeah, such as for the biostimulant production. And that's all from my side. Thank you very much.
Thank you, Iran. So if you just wait 1 second, we'll just see if there's any questions from the floor or online. Felipe, is there any questions online? Okay, anyone from the room? Any questions for Iransu?
So something that would make a difference.
From a statistical point of view, significant. Yeah.
There's no more questions. The next presentation, thank you so much. And we have Thomas. Just there we go. The formatting's okay. Over to you.
Thank you very much. Thank you, Emma. I will try to use this one. Usually I speak very loud, so just let me know. So yeah, I will be talking a little bit about the HTL technologies or the HTL activities and the related activities to HTL that we performed in this project. And I have to say that with this short presentation, of course, I'm only scratching the surface because out of this work package that I'm also presenting here, actually 3 PhD theses will come out. 1 already came out and 2 will come out later next year, hopefully. So there will be a lot of detailed information also to find later on. But yeah, I will be talking about how we use HTL to valorize urban waste. And just to briefly explain, if there is somebody in here that's not familiar with HTL, what is it? Is that you need to have water present at all the time. You need the high temperature. So typically we're operating close to the critical point of water or even above the critical point. We set out some ambitions for the HTL is that we need to have high energy recoveries to have a feasible process. In this, we had let's say a quantitative measure, which was 85%. So how much of the energy in the feedstock that ended up in the biocrude. This was also, let's say, one of the really first projects where we digged into these high inorganic feedstocks. So a more loosely ambition was to develop an HTL process that could actually cope with these feedstocks. I'll dig more into that. Now, of course, the HTL biocrude is the main product, but we also have side products such as solids that has a lot of phosphorus in it. And in this whole circular economy, we have to recover all the phosphorus. So we set a very ambitious target here to recover 95% of the phosphorus. Because we work with the urban waste, we simply have a wet feedstock already when we have it. Is there a pointer here? All right, here. So we get a lot of water, so we have to deal with this water here. We had a baseline in the project using thermal treatment for this one here, but we also set out some research questions if there are alternative technologies out there that can be used, and I'll dig more into that. And then, of course, the biocrude from HTL is just an intermediate product. It's not a fuel. So we wanted to produce a biocrude that was actually upgradable. And again, it's a little bit loosely defined. But we wanted to see, what does it take in purification to turn this biocrude here into finished fuels. Let's see, is it this way here? All right, so just overarching, we worked at different scales with HTL and lab scale, but also at continuous scale, rather lab scale, as Lasse mentioned. We had quite a learning curve here, was shown before the COVID here. And of course, we learned that there are large challenges with these urban feedstocks. And of course, scaling and fouling is one thing. But also when you start mixing things, like from home, when you start mixing mashed tomatoes and beef and water, and suddenly you have a bolognese. And this is the same thing in HTL. When you start to mix everything, you might get an emulsion. This is really what happens. So when you process these urban waste streams that has a lot of different stuff in there, different say heteroatoms, inorganics, you start mixing up things. So you don't get a clear water and a clear oil phase and a clear solid phase as you would like to. And I think quickly in the process of this project, we realized that here's a risk. So we had to design and install completely new separation techniques in this process that wasn't really accounted for in the beginning. And the aim was that we had to produce this high quality biocrudes. So of course, we were not the end of the project. There was a whole work package working on downstream upgrading that was waiting for high quality biocrude. So we had to produce something that really worked. But in the end, we managed, which I think is a major achievement, to produce more than 100 kilos of biocrude in what we call upgradable quality that goes straight into a hydrotreater. Then, as I said, here's the problem. Because everything is mixed together, but at the same time, we're very ambitious in separating out all the things. So we had to make some compromises. So first of all, when you have the biocrude, it's mixed with phosphorus. So again, the biocrude is not good. The phosphorus is not good for, let's say, circular use because it's mixed with the biocrude. So how do we separate all that? So really, it's a multi-objective operation to design and install this separation train. But the top priority was that we want to make an upgradable biocrude. Because if we didn't have the upgradable biocrude, there was really no process downstream. And so what was the consequences? Well, what we realized is that in this emulsion, we have more or less all the phosphorus. And I think we quantified 93% of the phosphorus, so we know where it's already at. So we had a KPI saying that this was 95%. So we were close to it. But when you start removing all the oil, you lose some of the phosphorus. And where do you lose it to? You lose it to the aqueous phase. And we know that we can recover it from the aqueous phase. So in terms of let's say the total recovery of the phosphorus, we didn't really manage the 95%, but we managed to identify how we're going to reach the 95%. At the same time, we get an upgradable biocrude. Now, the good thing is that when you start removing all the, let's say, contaminants from the biocrude, you get this solid product here that we termed a mineral product. And not surprisingly, this is where you have all the phosphorus. So it's a very concentrated phosphorus product. It has also most of the heavy metals, but compared to the feedstock, it has basically the same usage and the same potential. The good thing about using a high temperature process is that you destroy most of the organic contaminants. So we had it verified on polyaromatic hydrocarbons, pharmaceuticals, and so forth, and also on the microplastics that Lasse mentioned. So basically, we managed to produce an upgradable biocrude at the same time producing a byproduct, which has a really circular impact, which was very nice. Now a little bit on the microplastic, because that was an ambition early on in the project. But the problem is that there was no method for quantifying the microplastic. So with some colleagues from our wastewater engineering department, we developed a method. So you can imagine you have to remove everything that's not microplastic. So how do you make separation techniques and so forth? And then when you have the microplastics without everything else, you need to quantify it. And so in this case, there's a coupled technique between microscopy and micro FTIR. So basically with this technique, you can count all the particles, you can count the size distribution, and then with the IR data, you can also see what kind of plastics it is. And so we found quite a lot of plastics. I think in total there was 14 types of plastics quantified, size distributed, and everything. And then we looked at where the microplastic ends up and how much was destroyed. And in gross figures, we realized that almost everything is destroyed, which was very intriguing. And we know that some of the microplastics that are left are mostly polyolefins, which is by no means surprising because they are the most thermal recalcitrant. But again, a very strong number out of this project. So the question is, how do we perform based on the HTL in this project here? So I think I need to define something, and that is, when you do HTL and you run through the reactor, you get an oil phase and a water phase or an emulsion. But the fact that you have an aqueous phase means that you're losing some carbon to the aqueous phase. There must be some kind of equilibrium. And if you don't do anything, that carbon you lose to the aqueous phase, you can see that as a penalty. At the same time, if you add any process promoters, such as alkalis, you also lose that to the aqueous phase. So when you're ambitious on the energy recovery, you have to do something, because otherwise you're never gonna reach high energy recoveries. And so one of the things that can be done is to take this aqueous phase and then do a concentration. So you remove most of the water, any organics that is lost to the aqueous phase, you can bring it back to the process and thereby increasing the energy recovery. Now we had a baseline, which was thermal distillation, which actually works pretty fine because you get the concentrate, you recover most of your organics, you recover most of your alkalis, and you get a distillate, a clear water, which can be discharged. So that worked perfectly already. But the question is, are there any other alternative out there, alternative technologies that might perform as well? So as I said, we need to compromise, or we had to compromise in the project, meaning that in continuous large-scale operation, we looked at single pass operation mostly, and we identified an energy recovery close to 80%. So not entirely the KPI, but really close to. Well, we know from lab scale that when we start recycling all these organics, we increase the energy recovery, and we could actually meet the KPI in the project on smaller scale. And I'm almost certain that we can, let's say, transfer the observations here to the large scale and reach the same energy recoveries. At the same time, we did quite some detailed analysis on the nitrogen chemistry. So maybe you wouldn't believe it, but there is a good nitrogen and there is a bad nitrogen, especially for this emulsification and also for downstream processing. Iransu talked a little bit about it, but it's extremely important that we know how the nitrogen behaves in HTL. And so some of the things is, of course, you could do pre-treatment to produce low nitrogen biocrudes, and that would, let's say, ease the upgrading, less hydrogen cost and so on. But again, yeah, you might lose some of the carbon, but can we find some outlet or reuse of the carbon in the process that might be quite useful? And as I said, there will be a PhD thesis coming out on this subject at some point. Now, what is the alternative to thermal distillation of the aqueous phase? Now, in the project, we wanted to investigate the membrane distillation. But the problem is that membrane distillation is not so robust to the aqueous phase because it's also a mixture of many things, and especially suspended solids, remaining oils, and so on. So through some iterations in the project, it was decided to divide aqueous phase purification into two steps. And the first method was a filter up front to remove all the retained solids and oils. Now, again, if you just have a dead-end filter, it's also going to block. You can recover some of the fluxes by incorporating different operational procedures such as relaxation and backwash. And also, I think uniquely to this project is that there was an aeration process investigated. So you basically just blow air up front your filter to remove any scaling or fouling that you have up front, which allows the flux to be maintained. Now, the added value of that is that when you blow air through the aqueous phase, any ammonia that's trapped in the aqueous phase is also released. And based on quantification, we identified that more than 90% of the ammonia was released through this aeration. And basically, you could just trap that downstream of the process. So if we look at it, we have high carbon utilization in the biocrude. We have high phosphorus recovery in the solid product, and basically we could also have high nitrogen capture by looking at the ammonia stripping downstream of the aqueous phase. Now, when we removed all the dirt in the aqueous phase, we still have to remove all the excess water so we can bring back the organics. And here the second stage was then the membrane distillation. I think KIT came really far, found that like you could maintain high fluxes at a 60% recovery. I say you remove 60% of the water, even 70%. I think at 80% you start to see some wetting and some crossover of the organics on the membrane. And of course, you also see some fouling here, but you can also let's say deploy different operational procedures that maintain the high fluxes. And I can't remember the number entirely, but I think it was operated at about 1,000 hours. So quite impressive. And I think that brings me to the conclusions. And so through the process, we really gained a lot of experience, goods and bads, about HTL working on these high inorganic waste streams. We know that we can process it. We know that we can have high performance, but we still have challenges ahead that we need to solve. And then I think more importantly, we actually demonstrated that the biocrude can be upgraded, which is really the showstopper if you cannot. Then again, as I said, we have high recovery of energy and carbon. We potentially have high recovery of nitrogen as well. And we know that we can have high recovery of phosphorus. And then again, because it's a high temperature process, HTL might be the terminal process for many micropollutants that you will find in sludge and food waste, etc. And then we know that we identified a second efficient pathway for dealing with the water effluent in HTL. Right.
Thank you, Thomas. That was really interesting.
Good. Was I on?
Before you go away, we'll just open the floor to any questions, anything online, and anyone in the room. Okay, maybe people will think throughout the day and come back to you later. Thomas will also be chairing our panel discussion later, so he'll be up for question then as well. Okay, so we're over to Ellie.
Why it's not working? Okay, good. Okay, so you already heard from Iranzu and also Thomas how we can get a feedstock which is a bit problematic and a low value carbon containing feedstock and convert it through HTL into a nice flowing brown liquid which has a high energy content. Of course, can we already use this as a fuel? The answer is unfortunately no, that would be perfect. But unfortunately, we need to do an extra step in order to upgrade this and give it properties that are more closer to what we are using today in fuel applications. So HTL oil is a complex mixture. It contains of more than 20,000 different molecules. And although a great job has been done in reducing inorganics and also the heteroatom content by the pre-treatment that Iranzu showed, and also the HTL configurations that Thomas showed, they still some of it ends up in the oil. So it has relatively high inorganics content, and this can cause issues in the downstream upgrading in terms of catalyst deactivation. It contains some fatty acids that give it acidic properties, corrosion issues, high viscosity, and depending on what type of feedstock we start with, it has high levels of oxygen and also nitrogen when we talk about sewage sludge. These are some of the properties of the HTL oil that we got from Aalborg and Steeper, produced from the sewage sludge. As I said, very high heating value, and this is a big plus. But on the other hand, we have a high microcarbon residue TAN number, which is representative of acidity, about 100. As I said, inorganics, and we found out together with Steeper and Haldor-Topsoe and ENI and the other partners that this is iron for the most part, about 700 ppms. And when it comes to the heteroatoms, 10% oxygen, 2.5 nitrogen, and about 1% sulfur. We did a lot of analysis. Very good work was done from ENI on analyzing the oil with FTICR MS. This is a fingerprint, spectrum of the oil. And we can see that it has a lot of different components with the molecular weight ranging from 200 to about 600. The different colors here corresponds to different classes of compounds. So the greenish colors correspond to nitrogen-containing compounds with 1, 2, and 3 nitrogen atoms, whereas the red, yellow, and orange ones corresponds to compounds with oxygen and nitrogen atoms. And ENI did a classification of the different molecules into these classes, where we can clearly see that the highest concentration of compounds are compounds with nitrogen and oxygen, either 1 nitrogen, 2 or 3 nitrogen atoms combined with oxygen, corresponding to fatty acid amides coming from the feedstock. And also here, compounds only with 1, 2, and 3 nitrogen atoms, corresponding mainly to heterocyclic nitrogenated compounds. So we need to upgrade this oil. And here you can see the concept that we followed in the NextGenRoadFuels and that we have been working in the last 3 years. So the novelty of this approach was to combine an electrocatalytic hydrotreating step together with a thermocatalytic hydrotreating step in order to be able to upgrade this oil with the minimum use of hydrogen, let's say, in as mild conditions as possible. So the idea is that we start with the HTL biocrude. It first goes into an electrocatalytic hydrogenation step. And in this step, which happens at very mild conditions, room temperature 200 and from atmospheric pressure up to 10, 15 bars, with renewable hydrogen, we can partially upgrade the oil, hydrogenate unstable oxygenate containing compounds like ketones and carbonyls, and at the same time produce hydrogen. So in the second step, this partially upgraded HTL oil together with the hydrogen is fed into a second, more classical catalytic hydrotreatment that is done at more severe conditions, temperatures up to 350, 400, and 800 bars, and to finally produce the upgraded HTL biofuel. So the electrocatalytic hydrogenation was something that was investigated in TUM, where they build a high-pressure titanium cell with a Nafion membrane that allows to convert organic compounds without fouling and in a continuous mode. So you feed the organic substrate in the cathode side, water on the anode side. The water is split into protons that go through the membrane and hydrogenate your compound, at the same time producing additional hydrogen. So it was demonstrated in TUM that we can directly add hydrogen to organic substrates and produce hydrogen at moderate current densities and elevated pressures. Of course, we need to work in water, and the oil is organic. So by default, you create a biphasic mixture. They also did tests to show that it also works in a biphasic configuration where you have your aqueous phase and your organic phase, and you can hydrogenate the HTL biocrude. So electrolysis does offer a scalable, decentralized route to hydrogen addition. So conceptually, it could be something that is done in the centralized location, and then we have this more stable oil being transferred to a classical refinery for further upgrading. I don't want to go into too many details. They've done tests with several concentration of electrolytes, so different ionic strength in the cell. They saw that you can increase the rate of the hydrogenation without affecting the generation of hydrogen. And again, working in a biphasic solution, we are able to hydrogenate the compounds that we want. So then we go to the second classical hydrogenation step, which is done thermocatalytically. And this is work that was done by us, Haldor Topsoe on the catalyst side and Steeper Energy. We've done a lot of work that I'm not able to show, obviously, in this 10 minutes, but I wanted just to highlight that we also work on the development of new catalysts that are more suitable for treating this high nitrogen containing bio-oils, such as molybdenum nitride. So we worked on molybdenum nitride catalyst unsupported and also supported on different mixed oxides. We started with small lab scale tests, batch tests, where we worked with initially model compounds that contain oxygen and nitrogen, amides, and then with a real HTL biocrude that was sent to us from Aalborg to investigate, optimize the process, investigate the effect of operating conditions, reaction configuration, and also extent of thermal reactions. And I forgot to put a reference here. We recently published part of this work together with ENI and Steeper in Energy and Fuels. So I will skip all this part and then go on to the continuous tests that we run in the pilot plant unit that we have in CPRI. So it's a continuous unit. And what is nice about this unit is that it's equipped with two types of reactor. We have a fixed bed reactor and at the same time a slurry reactor connected to the unit. So we can run it continuously and easily check the effect of the reactor type in the entire process. So we first wanted to see this effect of reactor. So we ran one-stage hydrotreatment continuous tests with the HCl biocrude at 3 different conditions, 250, 290, and 350 degrees Celsius. Exactly the same reaction conditions, exactly the same catalyst in both reactor types, pressure 100 bars, and a hydrogen to oil ratio of about 1,000 on a volume basis. So what I'm showing here as an overview is the yield to the different products at the 3 different temperatures that we studied in the fixed bed and in the slurry reactor. Also with the black dots here, you can see the consumption of hydrogen in each reactor type and each temperature. What was nice is that in either type of reactor, so in both types of reactor, we got high oil yields. It started about 95, 98 at 250, and even at 350, we had about 90% yield in oil, so we did not lose it in gas, and there was also no extensive coke formation. We also saw we don't have too many differences attributed to the reactor type. We were interested to see what is the removal of heteroatoms. So I'm showing here how much of the nitrogen, the oxygen, and the sulfur was removed at 250, 290, 350, and again for the 2 types of reactor. Obviously, as the temperature increases, the removal increases, but we can see how resilient nitrogen compounds are. We have no removal in either reactor for 250 and 290. But if we go up to 350, we almost completely remove, or to a very high extent, the oxygen and the sulfur. And we managed to get with the slurry reactor a 54% removal of the nitrogen, which is pretty good for a one-stage process. And again, if I want to compare between the 2 types of reactor, we can see that systematically there is a slight but always higher heteroatom removal degree compared to the fixed bed reactor operation. So once we saw this difference between reactors in one stage, we wanted to run a 2-stage hydrotreatment test in our pilot plant. So we started with a biocrew feed. We put it in the fixed bed at 290 to do a partial stabilization. And then we fed the stabilized oil to the slurry reactor at 350, keeping again all the other reaction conditions constant in both of these reactors. And I'm comparing here just to showcase this, the removal of heteroatoms we achieved in the one-stage operation in the fixed bed, one-stage operation in the slurry reactor, and the two-stage process configuration. And it's clear that here we achieve the highest removal in the heteroatoms. As I said, oxygen and sulfur are not a problem. They can be easily removed, but here we achieved more than 80% removal in nitrogen, something which is very important for the further use of the biocrude, of the biofuel in fuel applications. And I'm showing here the properties of the best oil that we got from this two-stage hydrotreatment process. Here are the properties, of the feedstock, and here are the properties of the upgraded product. And we can easily see that we have a huge improvement. We increase, first of all, the heating value to levels that are similar to fossil-based fuels. We managed to completely remove sulfur and oxygen and 83%, as I said, of nitrogen. Also important is that we managed to demineralize, the oil. The iron content is almost completely removed. We also lose all the acidity of the oil and the microcarbon residue. Again, we ran an extensive set of analysis here to understand how the oil looks like. I'm showing here some results from the GCMS analysis that we did in CPRI. Here is the feedstock, where you can see there is a very high concentration of acidic compounds. We also have nitrogen-containing compounds, ketones, some aliphatics, and some aromatics. It looks completely different in the upgraded HTL oil. So we have a complete removal of the acidic compounds. We cannot detect them with the GCMS. We have a very high production of aliphatic, but also aromatic compounds. And if we look at specific molecules, we have a lot of molecules in the C10 to C18 alkanes range, BTX, alkyl benzenes, and also some alkyl naphthalene. We did a simulation distillation. Again, the results compared to the feedstock. The feedstock has 65% molecules that boil off above 350 degrees Celsius. In the upgraded oil, this goes down to 17%. We have a doubling of the diesel fraction from 25 to 50, and a tripling of the gasoline fraction from 11 to about 32. So overall, 80% of the oil is gasoline and diesel, and the rest we can use as marine fuel. This is all very nice, so we're happy that we got the process running. Of course, stability is a key issue in these processes. It's important also to demonstrate that we can run the process continuously. And this work was done by Steeper Energy in the Advanced Biofuel Center that they have in Calgary, in Canada, where they do a lot of different studies. Katerina, you know better than me on advancing the stability of the biocrude, checking the blending, compatibility, demonstrating the refiner integration, and generally investigating how the HTL oil can be upgraded and can be integrated also in refineries for co-processing options. So the guys in Steeper run the hydrotreatment process in their pilot scale units for more than 400 hours time on stream, and they achieved a very stable operation using a commercial catalyst and doing a two-step hydrotreating, one at 290 to stabilize the oil, and a final step at 400 degrees Celsius. So conditions similar to what we used in CPRI. Here you can see the properties, the yields, and the properties of the oils, the feedstock, the oil from the first step, hydrotreatment at 290, and the final upgraded product. And I was very happy, Katerina, to see that we got results that are similar. You also managed to remove sulfur, also a high percentage of oxygen removal, and also about 70-75% of nitrogen removed. Iron was completely removed. Also, viscosity went down. TAN was below detection level, so a very good fuel. At the end, here are simulation distillation curves. This is the one of the feedstock and the intermediate product, and this is the simulation distillation curve of the final product, where again, you can see that we have about 80% gasoline and diesel fractions, and the rest goes into the marine drop-in fuel. So we managed to show in these 3 years, I think that we can, it is, Thomas, an upgradable HTL oil. And we showed this in many ways. So it's a proof of concept that the sewage sludge derived HTL oil can be upgraded by hydrotreating, solving also the issue of the inorganics and the iron as this was removed during the upgrading process. And again, achieving significant improvement of the key properties, removing oxygen, sulfur, more than 73 up to 80% nitrogen removal, and eliminating all the acidity from the oil. Also important that we cracked it to the desired fractions. We got double diesel concentration and 3 times higher gasoline concentration than our initial feedstock. And work never finishes. There's still things to do in that respect. So the people in Steeper are distilling the product that they got in high quantities in order to analyze individually the different fractions and also check blending for use in drop-in fuel applications. Yes, and I think that was from.
Thank you. Really good timing, considering we were behind. Fantastic. Just before you sit down, we'll just check if there's any questions. Any questions online? Anyone from the floor? Yes, Robbie. Wait, I'll come over, run over to you.
Rob Weaven about PDG. Very short question about the electrocatalytic hydrogenation. I will not go into detail, but is that one published somewhere in a thesis? Will it be published in a thesis?
I'm not the right person to ask, I guess, but I will find out for you and let you know.
TBC. My question is, when can I use this fuel in my car, because I can't afford petrol anymore?
Can ship some
Yeah,
liters to you.
we'll talk about that in the networking session. Okay, thank you very much. Now we're over to Camille for the one question online. Sorry, Ellie, you're not free just yet.
Hello? Yeah. It's a question from Sakib Tor. With time, there will be catalyst deactivation during the HTL oil upgrading, which will limit the catalyst life and operational stability. Do you investigate the catalyst deactivation issues?
Not yet. It is something to look into. I don't know if Katerina, with the long-term tests, you've done some analysis on used catalysts.
So thank you for the good question. Definitely catalyst deactivation is happened due to the iron content of this biocrude. It's something that we have to address. And as Ellie mentioned, we have to do the mineralization in order to avoid further catalyst plugging active sites of the catalyst deactivation due to pore size plug or the use of these active sites for a different pathway and not the oxygenation or the sulfurization or the nitration. Now, if we go to the second pathway, and this comes to the test of the stability of the catalyst, we have got stable results at 400 hours of operation. We couldn't run further than that because we ran out of feedstock, and we couldn't see any catalyst deactivation during those 400 hours. Now, somebody may ask, we have to run for about 3 months to be able to give a refinery the reliable data that can ensure to them that these catalysts are going to last for 3 or 5 years, which is what a refinery normally like.
Yep.
Hours. So we ran different tests. The longest one we had in our pilot scale unit was about 150. And again, we saw no issues for that time frame. 400. Yep. More severe conditions. Yeah, also our problem, and that's why we stopped the test.
Yes, one more question. It's not precisely for this work package, but also it's a more collective answer. Sorry for my pronunciation, but the question is from Alireza Faraji, and she's asking about the toxicity studies related to the byproduct, so the biochar and hydrochar. So if we have any results on the toxicity of byproduct.
Well, the missing thing here is really what is the, let's say, the availability of the phosphorus and the nutrients and so on in the mineral product that we have. So based on the toxicity, future toxicity and so on, of course we get all the heavy metals in the mineral product, but on concentration, let's say based on the phosphorus and so on, we know worse than the sewer sludge that went in. But we know that we also destroy all the other critical contaminants in there. As I mentioned in my presentation, we have no medical residues, we have no aromatic hydrocarbons and so on. So I think overall the future toxicity and the toxicity in general is really low of this byproduct.
Thank you.
Dean has a comment.
And you can add destruction of pathogens and to those compounds. That has also been proven.
Great, thank you for that. So we'll move on now to Camille because we are running a little bit behind. But don't forget, we do have the panel discussion. So if there's anything else that's more of a general discussion, we can pick it up again at the end. So over to you, Camille. Thank you.
So hello, everyone. Thanks for your presence here, either online or physical. In the next 10 to 15 minutes, I'm going to be talking about the biodiesel blend stock production and the engine testing results, actually more into engine emission results, I would say. So let's start with the overview of the next generation road fuel and work package 4. The biomass that we used here was the biopulp, which is actually the organic fraction of the municipal side waste. So it was pre-treated, and then it was converted to biocrude, and then the biocrude was, as Ellie described, was upgraded, and then we reached to work package 4, which was mainly about production of the sustainable fuels and also marketing and development. That maybe Philippe in the following presentation would address that. So it was a contribution between Aalborg University, Good Fuels, and CPER Energy. And in this, we tried to look for 3 different objectives: miscibility and compatibility of the produced drop-in fuels and the oxygenated blend stocks, and using of these fuels that we produced in an engine. So for that, we considered 2 different scenarios. The first one was to see what is the potential of the biocrude itself to produce distillates, because we knew that the biocrude itself is kind of unstable because of the oxygenate that it has. So we tried to fractional distillate that to maintain the different distillation cuts here. And then another strategy was to firstly hydrotreat that to remove the oxygens in a mild hydrotreating condition at 320, 330 degrees C, and to see what is the effect of this mild hydrotreating on the properties and also the recovery. So firstly, initially, we observed that from 25 degrees, we reached to 60 degrees C, which is a big and significant improvement in the recovery. So we knew that we could obtain more of that distillates in the second scenario. But I will talk about the properties more in the following slides. So to produce the drop-in fuel or blend stock, we faced 2 different challenges. The first challenge was how to maintain and how to obtain actually the blending of that distillates that we produce, because in a conventional way, we get the fractions from this part, the diesel boiling point part, and then we mix them together. Then we mix it with a reference diesel, and then we calculate and we see the properties. But we wanted to actually do it the other way around, so we could kind of follow the EN 590 standard specification for the diesel to produce a diesel bioblend stock. Next slide will be about the multi-objective optimization that we use. We firstly distinguish different properties that were kind of limiting on the property side. And then we use the model to firstly calculate the blending of the distillate fractions, and then mathematically calculate the introduction of that blend to the reference diesel. So using this blend, we obtain the optimal fraction mixing, which we call it DM, distillate mixture, and then the optimal mixing of DM with the reference diesel. Here you can see the results of the first scenario. The problem with the boy crude and its distillate was that we saw the first blend wall, which was the sulfur content, in 0.5. So it means that we were not actually able to add any of those distillates to the reference diesel if we wanted to be on spec. And the second one was at 5 degrees, which was water content, and you can see the composition of that distillate mixture. So the action that we took here was that we didn't produce any on-spec fuel using the biocrude distillates, but we did a 10% biocrude distillate mixture for the engine testing results and engine testings actually. The second one was the hydrotreated or pre-stabilized oil. And as you can see, the sulfur content is moved from 0.5 in the previous scenario to around 10%, and that's because of the removal of the sulfur during the hydrotreating. And the first blend wall here was at 5 weight percent. It means that we could at least add 5% of the distillate mixture to the reference diesel to have an on-spec fuel. So here we did one fuel which had 5% of the bioblend stock and 10% of the bioblend stock. So we could have like 2 different samples here for the engine results. But before the engine testing, we did an aging and a stability test. We could see that, here we use biocrude and the distillate mixture of the biocrude and also the hydrotreated and the distillate mixture of the hydrotreated. In the 4 first weeks, we could see that a big difference and a big change in the HHV could be observed. And it was probably because of the condensation reaction and polymerization reactions that could happen. But one might argue that it's a good thing to have more high calorific value, but on the same time, the viscosity of the fuels changed significantly, which makes the handling and transportation and burning of the fuel in the engine way more difficult. So in the fuel combustion results, we evaluated 6 different combustion, the most important ones: CO, CO2, SO2, NOx, and 2 other. Here you can see the results of CO2, and as you might see as you can see, the difference in the CO2 is not significant. And that's because of the complete combustion reaction that happens in the engine. And one can argue that, okay, we are using the bioblend stock, but CO2 is not changing. But I have to remind that 5 to 10% of these fuels were from the carbon neutral source of fuel. So we were actually saving 5 to 10% of the CO2 into atmosphere. And here you can see the results of CO. Having the higher amount of oxygen in the fuel make the incomplete combustion. Prevent incomplete combustion. But while you have higher viscosity in the fuel, which was the case in the biocrude distillate mixture, it makes atomization of that fuel in the engine more difficult, and then the incomplete combustion will increase, so you will get more of CO2, of CO. And then the results of SO2 and NOx, you can see that in the on-spec fuel, these 2, we didn't get more SO2 because I mean, the level of the S in the fuel was less than what was announced by EN 590. But here in the bi-crude distillate mixture, we got more of SO2, and it's because of the higher in situ sulfur of that fuel. And the NOx emission actually increased. That was expected because as you can see, the sequence of nitrogen in the fuel, the higher nitrogen you have, the higher NOx you will get in the fuel. But we have to take that into consideration, that from this one to this one, I mean, from the bi-crude distillate mixture to the reference diesel, the difference was only 4.5%. So we were not actually increasing the NOx emission significantly. And the last two are total particulate matter and total hydrocarbons. And as you can see, the total particulate matter for the two first, for the upgraded distillate mixtures, decreased, and it's because of the higher in situ oxygen content, because oxygen can oxidize oxygen in the fuel can oxidize the soot, but when you have a highly unsaturated hydrocarbon, the radicals that can form while combusting can go together and can make bigger particles, so they will increase the soot formation. And lastly, the total hydrocarbons, you can see that by doing the upgrading, mild upgrading, we could decrease the total hydrocarbons, because the cetane numbers increase, and then it will decrease the ignition delay, so the hydrocarbons can burn more effectively in the engine. And lastly, it's because, as I mentioned before, the viscosity of the BCDM, which was the distillate mixture of the bi-crude, had a higher viscosity, so it could not burn properly in the, combust properly in the engine. So it could there could be more of hydrocarbons that were unburned at the end. So to wrap up, we point out some bullet points, which is the first one and the most important one, is that bi-crude stabilization is a key step before any further upgrading, because the upgrading, the pre-stabilization that you do will enable you to get more distillates, and also it improves the properties of the bi-crude. And then the physiochemical and elemental properties of distillates can be tuned by hydrotreating, because we can move that blending walls to further, so we can incorporate more of that distillate mixture in future by tuning the hydrotreating. So it is kindly dependent to hydrotreating, because the higher you go, the more severe you go to hydrotreating, the more chance you have to incorporate more of that distillate into the final fuel. And the oxygenation made the bi-crude way more stable, because it could remove the oxygen content. And then regarding the fuel performance, we did the test for fuel performance, but we didn't manage to compile the results and bring them here. But we could have some indications from HHV that the fuel is gonna perform properly in the engine. And yeah, that's it. That's it from my side.
Thank you so much. Before you sit down, I'll just ask if there's any questions. Any questions online? Oh, Steen, come over to you.
What was the viscosity you were targeting for atomization?
The viscosity of the upgraded fuel, and the reference was 2.5, which is the viscosity in EN 590. But the BCDM, this one, the bi-crude without any pre-stabilization had 4.5. So we were trying to push down the viscosity to 2.5. Yeah.
Thank you. Okay, if we don't have any other questions, we're going to go online to our speaker who's not there. So we're going to go across to Salim. Are you ready? So now we're going to hear from some related projects and related across the world. First, we're going to start at Aalborg with Salem, who's going to present to us about a project called Low Carb Fuels. And we just need to skip a few slides because should be okay. We'll get there. Because there's a time difference with our speaker from PNNL, and perhaps just maybe this time difference. And okay, just go through. There's a preview of their slides. Okay, here we are. Thank you so much. Hand over to you. Here's the speaker. Here's the microphone for you.
Hi, everybody. My name is Mohammed Salman Haider. Today, from the title, you can see like I'm going to talk about the challenges and achievements at Aalborg University, and then what I did in the PhD, and then what I'm doing afterwards. And what I'm not going to talk about is demineralization process, why we need it, what's going to be the effect of basic nitrogenates, iron porphyrin structures in the oil, and what harms they can do in the catalyst, during hydroprocessing or during pre-treatment routes. If we want to have acid washing or other techniques, that I will not talk about. Here, I will just talk about, and I will also not talk about the co-processing, what we're doing at Aalborg University. I'm going to only talk about the standalone continuous hydroprocessing of biocrudes. And then I will share the time lapse when we started in 2019 and then where we are now. So let's see over here. So here you can see it's advanced biofuel group at Aalborg University. And then we do all this pilot plant testing with the HTL biocrude. We produce biocrude. You already heard when it's an intermediate product, we have to refine it so it can be used for applications such as diesel fuel, such as aviation fuel. So we need to refine it to a great extent because today I'm talking about the nitrogen-rich HTL biocrudes. So here is I think, okay, I don't know how it's going to turn with the laser light, but on the right-hand side, you can see the hydroprocessing team at Aalborg University. So it's me, Daniel Castello, our colleague, and then Laser Rosendahl. He's not here. And then we are working on all these kind of feedstocks, which are converted into HTL biocrudes, and we work on the continuous hydroprocessing of these biocrudes. This is a continuous unit at Aalborg University. And then usual throughput that we go up to is 80 ml per hour. It can go up to 150 bar of pressure. We can use it in series or in parallel. And then that's the general scheme of the catalyst in the reactor bed. So at the time lapse, I will try to tell you 4 different projects. So the first project when we started the hydroprocessing activities at Aalborg University was for refinery. And then at the end, I will talk about this low carb fuel project on which we are doing the hydroprocessing activities as I speak now. So before starting, I will let you know what are the main challenges during hydroprocessing. These are some of the challenges I have written, but there are 2 main challenges with these biocrudes. One is the immediate plugging of the reactors. That's one of the biggest challenge. How we can suppress the coke formation that happens not due to the metals, because we have metals in the oil, it's going to cause fouling anyways. But how we going to suppress the coke formation, which led to the reactor plugging much faster. And then the last thing, I'm going to talk about the nitrogen. Why nitrogen is a challenge, and then where we are now at Aalborg University. So in early 2019, we started this project for refinery. We were doing some of the activities on hydroprocessing. So 5 months, 3 failures. The maximum continuous run was achieved for 10 hours in 6 months. That was, we tried every route that is written in the literature, every possible scheme with a commercial catalyst, but that ends up in plugging within 4 hours, 2 hours, or after 10 hours. So then we start rethinking the whole process to understand what are these HTL biocrudes, because we have a lot of different feedstocks. But instead of looking into this reductionism mechanism, reductionism is something when you see at a thing at a very small scale, but you don't get a link of overall thing. So we need a holistic approach to get to the temperature, like suitable hydrotreating temperature. When biocrude sees this hydrotreating reactor, we don't cause plugging. So after that, that was the whole work. So biocrude, as Ali already spoke, it's highly complex. We have highly reactive compounds like carbonyls to least reactive like polyaromatic hydrocarbons. So it's very diverse in nature. And then they are not thermally stable. That's one thing to note. So what to keep in mind? So because I spoke like we need a holistic approach. So what we're doing at Aalborg University over the years, it's two approaches that we're using. One is detailed molecular understanding of HTL biocrudes using FTIC RMS, where ENI is helping us, and then GC by GEC, where some of the work is also carried out at TOPSI. And then, of course, the last thing is thermal instability of HTL biocrudes. Because combining these two, we will know for sure what will be the starting temperature when the biocrude is going to see the catalyst, and what temperature we should run in the first stage to suppress the coke formation and get longest ones. And of course, a little bit of knowledge for the catalyst is also worthy to have. And then as I'm talking about, these different classes of compounds, they have different temperature ranges. If you go beyond that, you will definitely form coke formation. So after having all that knowledge and put it into context, at the end of between 2019, end of 2019 to 2021, which was a core part of my PhD too, we work on spirulina algae biocrude, sludge biocrude, and wheat straw, achieve continuous hydrotreating operations for 335 hours for spirulina, 165 hours for sludge, 215 hours for wheat straw. In all cases, biocrude was finished. No sign of coking, plugging, anything was observed. And nitrogen removal, why it is necessary? Because for now, nitrogen 2 ppm is a safe limit for already approved fuels. So it means, and I have talked to a lot of people from ASTM standard, who are, so it seems like we have to go toward that robust things. We have to follow that 2 ppm thing. Still now, there is no approved standard for HTL biocrudes, but we're going to go toward that because they are so conventional on these things. So, but what's the problem? The problem is when we talk about nitrogen removal, it's not like in fossil crudes. Nitrogen is homogeneously distributed. Even you go at 400 degrees C, do the hydroprocessing, 90% or 98% nitrogen is removed, but nitrogen is homogeneously distributed in all carts. For example, in case of spirulina, but we have seen it with every biocrude during the hydroprocessing. So it was homogeneously distributed between diesel, jet fuel, and bit of what we call, the residue. So it means like we have to reduce nitrogen in the overall system to make it so we can use it as a jet fuel. So at the end of my PhD, I was able to achieve complete denitrogenation. And okay, we have achieved it. We know how to do it. And so we don't see it as a problem anymore. But the one thing that we're doing right now, in the next year, we're going to do in the low cost fuel project, which is our next project. We're going to produce the liters of fuel so we can distill them, because here one sample was produced, but we were not able to distill it. So we cannot see, the whole distillation cuts, jet fuel or diesel. That's the next plan, but we achieved complete denitrogenation. And then here the starting point was 4% of nitrogen, something like that. So these are the distillation yields that we got in the high flex fuel project. So as expected, with the jet fuel and with the sludge, we get more diesel for the sludge because we have long chain fatty acids over there. And then for the straw, because it's come from the lignocellulosic, we got more of this residue above 350 degrees C. So in the next gen road fuel, which you heard in past hour, so all that learning has been used over here, and then biopulp biocrude was run for 600 hours. But here the project aim was to produce fuel for the marine fuel application or others. But here the target was to achieve complete hydrodeoxygenation. So the unit was run for 600 hours, and then, of course, here we also studied deactivation due to nitrogen and all other things, but I will get into that later on. So this is a project that we are running at Aalborg University right now. So it targets all these jet fuel, diesel, and marine fuel. And these are the partners which we're working together. These are different work packages from standalone upgrading to co-processing. And in this project, we have been able to run it for 1928 hours, around 80 days, continuous upgrading of STL biocrude from food waste. And then here the main aim was to study the catalyst deactivation due to nitrogen and the effect of metals and all those sort of things. And yes, we did go to 400 degrees C. And next year the plan is to achieve complete denitrogenation on a relevant scale and study the fractional cuts, so we can say for sure, what tier or level we're going to be in future for this downstream processing. So in conclusion, I would like to say that two things: comprehensive knowledge about molecular structure of STL biocrudes and catalyst is vital if we want to do the continuous hydroprocessing of STL biocrudes. Catalyst deactivation due to coking can be suppressed by identifying the thermal instability, at what point STL biocrude is thermally unstable, and by identifying the highly reactive organic species present in that biocrude. STL plus optimized longer continuous hydroprocessing are possible and can produce drop-in fuel such as SAF, diesel, or marine. Complete denitrogenation is still an ongoing topic, but I told you we have achieved it in one sample. And then over the years, I have been working on different type of biocrudes. And then we are more than confident to achieve it on a relevant scale. And beginning of next year, we're going to start it with the food waste. And yeah, that's what's going on at Aalborg. If you have any question, please let me know.
Thank you, Salim. Thank you very much. I'm going to suggest that for you, questions come in the networking session. So Salam's going to be here. So if anyone, unless there's anything online, because we're running over it's not your fault because of the IT things. But yeah, if you've got anything any questions for Salam, he's going to be here until the end. So, and there'll be a chance to talk. Now we're going to go across to the US, and we should have Mr. Wang online. Can I hear you?
Yes, can you hear me?
Hey, hello.
Okay,
Nice to see.
hello.
Hi there. Let's just get to your presentation. And I think maybe would you prefer to share your screen, or I can click through the presentation on behalf of you?
Yeah, let me see if I can. Maybe it's easier for me to just give me a second.
Otherwise, I'll just go through. I can get your presentation, and if you just tell me when you want to change the slide. Oh, look, there you go. You've done it now.
Okay, so can you see my slide?
So thank you so much for logging in. I know it's early over there, and
no problem.
So Humin's calling in from PNNL.
Yeah, thank you.
Pacific
Thank you
Northwest. Thank you.
Okay. I guess I can start it, right?
Go for it.
Okay. First, thank you for the invitation to give this presentation. And as you see here today, I will give you a very brief introduction of PNL and what we're doing here, and some recent highlight on hydrothermal liquefaction study. But I will spend most of the time talking about biocrude upgrading, especially co-processing in refinery. Very brief introduction of PNL, and We are one of the national labs under Department of Energy of United States, and the PNL have more than 5,000 staff members and with 1.2 billion yearly budget. And we are very proud of many innovative technology we develop. And as you see here, there's more than 200 companies with PNL roots. So, and PNL, we're doing a lot of chemical and material science, biological earth sciences, and also computation and mathematical sciences, and also engineering R&D as well. For bioenergy technology R&D and PEL, we focus on process that convert the biomass and the waste into chemicals and the biofuels that are infrastructure ready. For instance, gasoline, diesel, and especially jet fuel, which is our kind of focus in recent years. We are working on advanced biotechnology, catalysis, and thermal processing. Here we just show you one of the kind of example that when we're doing catalyst process development, we have a set of instruments starting from high throughput catalyst screening to small scale catalyst testing to large scale process development and demonstration. So we have a whole set of a reactor system in different scale to support our catalyst process development. For our bioenergy technology R&D and PEL, we are very proud of many technologies we are advancing, but something I would like to share today, like for instance, I guess you may know from news that PEL worked with LensTech to develop that ethanol to SAF process, which is currently commercialized by LensTech under LensJet company. That is ethanol to ethylene, followed by oligomerization to olefins, and finally hydrogenation to produce jet fuel. And also, of course, PEL we are also working very extensively on hydrothermal liquefaction process and also the bicrude hydrotreating, which is the topic of my talk today. For PEL, we are continuous advanced HTL technologies. So my colleague Mike Sorsen ran that last year on this workshop and really shared our the progress toward HTL process. And I would like to just give you some kind of what really happened in last year about the overall HTL. So, as you know, the PEL we are publishing because state of technology for the HTL process, including our major our improvement on the HTL process. And we are continuously making significant cost reduction in our modeled ST and modeled SOT and cost for HTL plus upgrading. And which is the most important part is reducing the modeled heat exchanger cost and increase its robustness, which contributed the most of the cost reduction we achieved in last year. At the same time, we have developed a sulfur-resistant and robust catalyst for CHG catalytic hydrothermal gasification and HTL aqueous fraction. That we know that another byproduct from HTL is aqueous fraction, which contains a lot of useful carbon. So we were able to, and also the major challenge of that process is it has a lot of sulfur that will kill most of the metallic catalyst. We were able to develop a sulfur-resistant catalyst to really convert, utilize the carbon in aqueous fraction from HTL. And for upgrading part, as the previous speaker mentioned, that the nitrogen is really a big problem, and also the jet fuel require below 2 ppm of nitrogen. And at PEL, we were able to really improve the deep nitrogen removal in jet fraction. And I would like to really point out that with one of our technology, we are able to reach like below 1 ppm of nitrogen in jet fraction. And also, I agree that this is really a big challenge, and we are going to really put a lot of effort on this part as well to really reach nitrogen requirement for jet fuel and other fuel application. And also, Mike Sorsen shared last time that we learned that diesel fractions produced from HTL bicrude really have some cold point problem. So this year we were able to really address this issue and improve the diesel properties regarding cold point. So, but today we'll be what I'm talking is about standalone hydrotreating, that we were able to demonstrate 1,000-hour stability and also all those deep nitrogen oxygen removal to meet all the specs. But today I would like to talk about the co-processing, that how can we really process the biochar in existing refinery, use existing catalyst, existing instrument, and existing process without much modifications, therefore without much capital investment. Because by doing that, we can leverage existing infrastructure, therefore significantly reduce the capital cost for overall HTL plus hydrotreating process. So at NGRF, we have a project working on co-processing, and we're working both for fast pyrolysis, calyx, fast pyrolysis by oils, and hydrothermal liquefaction by crudes. And for this project, so we we kind of identify some major risks or knowledge gaps for co-processing, and really our project focusing on narrowing this knowledge gap. For instance, we believe that feedstock quality consistency and the biogenic carbon incorporation and the impact to refinery chemistry, catalyst reactor, and fuel quality, and also how can you accurately check the mirror biogenic carbon in a product and in a process, and also what's the economic and environmental benefits to both refineries and the biorefinery for co-processing. So we're trying to narrow all those knowledge gaps through extensive R&D. So this is one of the projects that we are working together with Unreal and Los Alamos National Lab here at the United States, and we are, as I mentioned, we're working on both CLP and fast pyrolysis and HTL routes. And Unreal is more focused on co-processing in FCC unit, and the PIA is working more on co-processing in hydrotreating hydrocracking unit, and the Lano is more focus on develop the biogenic carbon checking method. So we are supported by a strong IAB and industry advisory board, including refinery and also universities and other catalyst and providers. So at PIA, we are really focusing on co-processing in hydrotreating. I'll skip this slide really quickly, and we are doing different FISO feedstocks, biomass feedstocks, and doing detailed feed characterization and measuring hydrotreating performance with more than 300 hours time on stream to get a steady state operation. Focus on hydrotreating, hydrocracking, performance, including especially on hydrogen removal and hydrocracking to maximize diesel yield. And we're doing a few analysis and also detailed catalyst characterization to understand the catalyst deactivation and also other related aspects. So first, I would like to just quickly share that we were able to demonstrate high biogenic carbon incorporation for biocrude co-processing, as shown here that if we co-process VGO with HTL biocrude. For specifically, this HTL biocrude was generated by from a hydrothermal liquefaction of wastewater sludge. And here at roughly 5% blending through a hydrotreating hydrocracking two-stage process. This is not really a deep hydrocracking, it's a mild hydrocracking, and we were able to demonstrate more than 97% of carbon in biocrude was incorporated into the final fuel products. The 3% was lost in gas product. And the diesel fraction after this two-step process, we were able to show that we reached, the sulfur requirement and those other requirements, and also a higher center number, which is, makes sense because biocrude it really contains some nice diesel fractions, and also a high biogenic carbon in contact in the diesel fraction as well. So as the previous speaker mentioned that really nitrogen is the biggest problem for biocrude because it contains around 4 to 5%, and we definitely see the competition between sulfur nitrogen oxide removal during those hydrotreating step, and this is critical. And we have to deal with nitrogen in the low temperature hydrotreating pretreatment step, therefore to enable the high temperature hydrocracking step to get a higher diesel yield. And we were able to demonstrate that by mitigating that nitrogen problem, we can enable co-processing in hydrocracking. At the same time, we are kind of diving into this nitrogen problem and really to provide kinetics and further to provide a reactor model development to enable to predict the biocrude co-processing performance in both standalone hydrotreat and co-processing configuration. So we are kind of primarily focused on some unique nitrogen containing species in biocrude, for instance, biocrude amide, as I'm showing here. Sorry. So this biocrude amide and it's a harder HDL mechanism is not really knowing. So we spent some time to really figure out that what's the reaction network of this specific molecular, and also compare the kinetic of this molecular to other oxygen, nitrogen, and sulfur containing species was normally seen in biocrude. By doing that, we can really measure all those kinetics parameters and apparent activation antigens, and we will use all those information to and we've developed a kinetic-based reactor model for co-process, which is Aspen high-6 refinery based on Aspen high-6 refinery model. And we further studied what's the impact of co-processing to refinery catalyst. So which agrees with what claimed from the previous speaker. For instance, that we are using HDS model compound to really accurately measure the activity of catalyst after a fresh catalyst after diesel only hydrotreating diesel with biocrude with co-process with different type biocrude, for instance, raw biocrude, pretreated biocrude, and also the biocrude hydrotreating with a guard bed. We were able to show that how the raw biocrude really caused a significant deactivation of the catalyst is mainly because of the not only the falling of catalyst by inorganics, which form a layer, encapsulates the top bed of the catalyst, but also form a coke and extra coke on the catalyst bed. And by doing pretreatment biocrude and also use proper catalyst guard bed, we were able to really show that we can mitigate the catalyst deactivation, which, as shown here, that has no loss of catalyst activity, maintain the surface area, and also almost no falling on the spent catalyst. And we published this result recently in Energy Fuels. If you are interested, please have a look. Further, we did TEA to really understand that what's the impact of co-processing for refinery and biorefine, as shown here that by using co-processing, we can enable roughly $0.3 per GGE of cost reduction for co-processing. This for biocrude upgrade. This is mainly because of the capital cost saving because we use existing infrastructure. At the same time, we also did refinery impact analysis for co-processing biocrude and VGO in mild hydrocracking unit, and the results show that with ongoing R&D, the model the break-even value for sulfur bioil HTL biocrude will be greater than the modeled cleaning price at 2022 design case, really showing that it's possible that refinery can use biocrude as profitable feedstock. So next is that we know that for co-processing, another biggest challenge is that how can you accurately measure your biocrude content in your product, and therefore to claim the credits, and also how can you monitor the distribution of biogenic carbon in different streams, therefore to help you to understand their fate during co-processing. So we are here that this work is led by Leno, and PR is part of this team, and we're developing both stable isotope method, which is like delta carbon-13 carbon-12 ratio method to really measure the biogenic carbon content. The beauty of this method is that it's kind of stable isotope method that with certain technology we can do online quick checking of those biogenic carbon in process. And you can see those recent publications on this method down here. At the same time, we are also developing carbon-13 method. We know that for carbon-13 method, AMS is a gold standard, but that's really too expensive for a refinery to operate at their site. So we are developing liquid acetylation counting method, which we call LSC method, and we are making a lot of advancement in for this method. So we believe that by combining those two methods, that we are relatively low cost and deployable, that we can meet refineries' requirement for both online quick checking of biogenic carbon and also the accurate measurement of in the final product to ensure the quality. So hopefully I showed you today that at the PNL we are working on, we are continuous advanced HTL and hydrotreating part to really convert wet waste to useful fuel product. For co-processing, we demonstrate high biogenic carbon incorporation, and also we believe that by really take caring of HDN, we can manage the head atom computation and removal, and therefore enable the deep nitrogen sulfur oxygen removal from bi-crude to enable the fuel production meet the spec. And we can manage catalytic activation, and we believe that co-processing will can be beneficial to both biorefinery and the refinery. And also we are developing isotope method to really measure the biogenic carbon contact in products in the process. With that, I would like to acknowledge, the support from Department of Energy, especially the Bioenergy Technologies Office, and also the team here, and really make all those work happen. And really appreciate your time. And again, thank you for the invitation to be able to share some of our work here at the PNL. And if you have any questions, please let me know. Thank you.
Thank you so much. That was great. And thank you for the early morning. You don't look too tired. That's great. Does anyone have any questions here in the room? Is there any? Oh, okay. We have a question here for you.
Hi. I believe the Metro Vancouver HTL unit comes from the PNNL technology. Maybe you could say a word about it?
Yes, so this is, you're right, PN is really helping the Metro Vancouver, HTL unit demonstration and also supporting the upgrading as well. So I guess that's all I can say. That frankly, I'm not really knowing much about the Metro Vancouver progress for now, but that's that's all I can say. Sorry about that.
Thank you. Thank you for sharing that with us. And it was a pleasure. You can, of course, stay online and watch the rest of the presentations if you want to. But we're going to move over now to our next presenter, who's coming from Amsterdam University, University of Amsterdam, Mr. Shiju. Here we are. Hello, nice to meet you. Thank you for coming. I'll just put your name tag here and pass you over the microphone.
Yeah.
Yes. Okay. Thank you very much for the invitation to be here. Thank you, Professor Rosendahl, for the invitation, and nice to be here to talk to you, all of you. I know that according to the schedule, my talk is already finished, and I'm standing in between you and coffee. So I will try to keep it very short. So basically, I'm working at the University of Amsterdam. Sorry that the fonts came to be very small now, but I think we can still manage to see this. So we are actually, situated right here in Amsterdam, not in the city center, bit away from here because the municipality decided all the dangerous stuff should not be in the city, it should be away from the city. So we are in outskirts, but you are welcome. If you have time, you are welcome to come and see our facilities. So basically, we actually started the hydrothermal liquefaction as a curiosity a few years before with a few master students and a very little amount of money from the university that was only enough to do a few dinners for my group. And so it was very small scale. But later we were able to get support from booking.com and also Kuwait Petroleum right here also in Netherlands. And Kuwait Petroleum has a strong knowledge and technical base in about the fuels and hydro treating and also ASTM conditions and all those things. So it was very, and also they have one of the largest aviation fuel side branch actually. So it was very nice to collaborate with them. So basically we did the liquefaction in batch reactors to start with, and with organic material from Waternet. Waternet is actually the wastewater and drinking water company in Amsterdam. They have quite some organic waste that they sieve out from their water treatment plants. So we actually started with that and later moved to plastics. And as I said, also, as Professor Rosendahl said, it is not, HTL is not just the reaction, it is, I would say, more than that, and it is more the surrounding about the waste collection, treatment, and downstream operations, as you all know. And we also have, knowing that, we also have looked at what are the volumes of organic waste in Amsterdam, which is actually, you will see that it's not too much. From Amsterdam households, it is around 100 kilotons per year. And then what we do that right now is simply burnt in waste burning facilities here, like Meerlanden and Atro and Reneve. So actually it costs 119 euro per ton to simply burn this the organic waste. And then from food industry in Amsterdam, there is another 140 kiloton organic waste, and also the wider municipal area around another 140 kilotons. So that's all the organic waste within Amsterdam. So if you compare that with the fuels, so later on we could get also some agreement with Transavia and KLM, the Dutch airlines. And the people from there told me actually that if they want to move the flight, one of their planes in runway for a minute, not even flying, it already cost 1,000 liters of aviation fuel. So compared to that, you will see actually that these volumes are quite small, what we can get from Amsterdam. But so that also means there should be a bigger emphasis on waste collection and looking at the transport. And then comes the question whether you should transport the waste as solid waste or whether you should first convert it to oil and transport actually. So that's all these questions come from. And we actually were supposed to look at a bigger project covering all these aspects and with funding by Transavia and KLM. But that was just before COVID started, so we had to stop the project. So as you know, all the airlines went into financial trouble, and we hope we can restart that at some point. I will not go to this, you all know this actually, familiar that. And then we started the project with local plastics recycling companies for looking at chemical recycling of plastics with HTL on a small scale. And as you know, the plastics is getting a bigger and bigger problem. And if we look at what is the amount recycled, it is only below 10% of the total amount of plastic waste. A lot of plastics is simply composted or landfilled or composted. So this is going to be a bigger problem in the future. In 2019, there was 460 million tons of plastics, and the projected growth of plastics is going to be 3 times more by 2060. So it's going to be a bigger amount. Of course, this actually really prompted us to look into that area as well, as I said, with local plastics recycling companies. And then we looked at the plastics which are not suitable for recycling by mechanical recycling. So at the end of mechanical recycling, then you still have these plastics which are not amenable to mechanical recycling. So can we do the chemical recycling by HTL? And that also brought us for a new project from Horizon Europe this year, and which actually looks at closing the loop of the plastic in the plastic life cycle. And the objective of this project is to valorize a wide range of unsorted plastic and textile waste. And we are looking at quite some a few routes here, including pyrolysis, gasification, and enzyme fermentation. So the idea is actually to take the waste plastics that include polyethylene, polypropylene, polystyrene, and so on, and also waste textiles, and look at different routes, compare them in both technological as well as economical and as well as life cycle point of view. And this is overall 20 million euro project. And for HTL part, only for HTL part, which is done by me at the University of Amsterdam, we have around 1.6 million euros, which is quite significant. I think, of course, not enough money, maybe looking at the wider picture of the challenge, but still something to do. This is the consortium, which involves almost 20 partners, starting from Circe and Urbaser, Ascatec, Cogersa, and so on, and including Total Energies and a few textile companies as well. Here also you will see that including the polymer companies, waste recycling companies, and so on. So there are all partners covering all value chains are represented in the consortium, typical of the EU projects. And as I mentioned, we are looking at different routes and same hydrolysis, gasification, liquefaction, and microwave-assisted pyrolysis. And the objective in liquefaction is actually, as you can probably see here, to take the waste streams from of polypropylene, polyethylene, and polystyrene that comes from the Spanish waste recycling company Cogersa, and to convert it to synthetic oil by HTL. And this synthetic oil will go to the Total Energies, and they will actually upgrade it and crack it and make olefins again in the project. And these olefins will be again used for making polymers by the polymer companies and other compounds. So this the loop will go like as a closed loop. So that is the overall idea of the project. So we actually only started recently this month, the last month, and we are this is typical of plastics waste that we are handling. This comes from Cogersa again. As you can see, it's a mixed shredded plastic waste, which will go to our HTL reactors. We have both batch HTL reactors with different capacities, as well as a continuous HTL reactor, of course, at a much lower level compared to the facilities maybe in Aalborg and other partners, but still we can do some work here. And we also collaborate with local companies, local engineering companies, and the idea is that by the end of the project, we will build a pilot facility for waste plastics, actually. And so with that, I would like to end, but of course, it is nice to be here and nice to learn from previous projects and previous experiences. And I also hope that we can collaborate within this framework. We can collaborate in the next future and also learn from your experience so that we don't do the mistakes from again. And we can, of course, reinforce each other. Thank you very much.
Thank you so much. That was a really, really interesting presentation. And I hope, yeah, wish you all the best of luck. And of course, yeah, there's a big consortium here as well, ready to get on to the next project. Okay, thank you, everyone. Okay, so I hope you had a nice break, refreshed, enjoyed those lovely healthy snacks as they were written to me in the email. Now we're going to look at market scenarios and commercial pathways. So we're going to hear from Felipe and Ling. Ling has come all the way from Canada, so welcome. So Felipe is starting. I'll put his thing up.
Hello, good afternoon, everyone. So after so much of hard science, now a little bit of legislation to relax. So we can go from that. Actually, this work package was related to the market scenarios and commercial pathways. So good technology, but how can we bring that to the market? Not only the fuel that we propose to produce, but also the technology itself. How does that insert into the value chain? How we can benefit from the legal frameworks that is out there and on. Basically, this activity was split between good fuels that I'm representing here and also steeper energy. And also some input from NE and Topsoil. But of course, that we received information for all the work package so that we could design our assessment as such to cope with the properties of the technology that we are discussing here. And why is that important? And how should we do that? So how we insert or bring this technology or fuels into the market? So first of all, we need to understand how big is the market or which market that we should go for. And for that, we need to understand the transport energy scenarios because not only today is important, but also the future projections are crucial to understand how we should move forward and also understand which countries or places are more suitable for the uptake. So which environment will provide a more friendly space so that we can bring this technology into application, into deployment. And yeah, as you might imagine, is not a single criteria way of addressing it. It's a very complex environment. It's a social environment. So it's expected to have an influence from different aspects, such as legislation, current technology development, value chain positioning, opinion from the stakeholders. So to identify the most suitable places for that, we came with a multi-criteria analysis. So we try to leverage all the aspects as such we can bring in a consolidated and solid choice. Among the countries that we addressed it, we found that the Netherlands, Germany, and Sweden were the most favorable for technology deployment, but also for fuel uptake into the market. And then in a second stage, or parallel to that, we conducted, and Steeper did that part very nicely, actually. They conducted an extensive interview with more than 40 stakeholders, not only for the countries that we have mapped, but for all other countries as well, so that we could have different perspectives from the value chain. And what is that important? Not only for mapping the relevant stakeholders that might influence the deployment or the uptake of the fuel, but also to understand the value chain and see what are the unique selling points of our proposition so we can valorize them while addressing or selling the idea or pitching or bringing or lobbying. It doesn't matter how we put that forward, but the importance that we gain knowledge on how we can move forward. First of all, so how we understand the market. As I mentioned before, not only today's market, but mainly future markets, because we are addressing energy transition, and it's not only about today, but